All right, we are recording. For those of you guys at home, welcome back, and thanks for being on the meeting. For those of you guys on the meeting and in class here with me, we're going to continue with talking about exponents. Today, we're going to talk about scientific notation, which is a way to write really big or really small numbers in an easier form. We kind of talked about that yesterday, where we had like the speed of light was 299 million something meters per second. So we rounded that off to 300 million, and then we wrote it as 3 times 10 to the 7th, which is an easier way of writing that big number. So here is the presentation. As usual, they have a little 2.5-minute intro video about scientific notation, and we're going to pause a couple times and talk about what they're talking about in more detail. So here we go.
What is scientific notation and why is it used? Think about this question during the lesson. Louisa is researching the approximate distance between Earth and the Sun. Her father told her that the distance is 9 296 thousandths times 10 to the 7th power miles. An astronomy book said the Sun is 92,960,000 miles away. Which distance is correct? The distance stated by Louisa's father or the distance in the book? Louisa's father used scientific notation to express the approximate distance because the distance is so great. Numbers in scientific notation have two factors. The first factor is always a number greater than 1 and less than 10. The second factor is always a power of 10. Why is it important to keep some of the digits from the original number instead of using only a power of 10?
All right, so let's look at these. So which distance, we're thinking about which distance is correct. What do you guys notice? Brandon, can you see my mouse cursor at home? Or is my mouse like my pointer arrow?
Yes, yeah.
You see that on the screen? Okay, cool. I didn't know if my pointer actually showed up for you guys or not at home. Okay, so what do you notice about this number right here and this number right here? Hey, what's up? Good morning. What do you guys notice?
It's kind of the same, but that one is in decimal form.
Yeah, good job. I got people on the meet and here in class that are both saying the same thing. Like it's kind of the same thing, right? It's the same numbers. 9296, 9296 are in both of these numbers, right? So we're going to see here in a second, they're going to explain that these are actually the same thing, okay? These are actually two different ways of writing the same number. But first off, let's talk about scientific notation. What is required? All right, so they gave us two things that are required. Here's the first one. We always have a number greater than 1 and less than 10. What that means in a different way to say that is there's only one place that is left of the decimal, right? There's only going to be one number. It's going to be one number, decimal, and then some decimal numbers, right? 9.296, or it could be 7.60. Well, it wouldn't be 60, 7.61 or 3.7. It's never going to be 0 point something, and it's never going to be more than 9, right? It's never going to be double digits. You're never going to have 26 point, like you wouldn't have 92.96. You're always going to write it with the decimal after the first number, right? Because if we wrote it 92.96, we'd have to write it 10 to the 6th. So that's the rule for writing it. You're only going to have one number left of the decimal, all right? And it's going to be greater than 1 and less than 10, meaning it can't be a 0 and it can't be 10, 11, 12, blah, 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 because that's more than 9, right? That'd be two numbers. So one number left of the decimal in the ones place, and then the rest of our numbers go in decimal form. And then the second factor is always a power of 10. It is times 10 to the something, right? And this exponent right here is going to tell us how many places we need to move the decimal. So we'll talk more about that in a second. But the times 10 to the 7th is going to tell us we are going to move the decimal point 7 spaces to the right. So let's keep going.
You want your estimate to be close enough to make accurate calculations or comparisons. For instance, 9 and 296 thousandths times 10 to the 7th is more than 9 times the size of 10 to the 7th power. Write the number that's in standard form in scientific notation. How many places do you need to move the decimal point in the second number to write it in scientific notation?
All right.
Select your answer.
We can't see this. Let me pull up a Jamboard. We can't write on this screen, so I'm going to pull up a Jamboard here. 92,960,000. Let's share this tab instead. Let's go over to our Jamboard. So we are going to prove here that these are the same numbers. 92,960. It's asking us how many spots do we need to move the decimal point in order to write this number in scientific notation. So our decimal point's right here, right? If we technically have a 0.0 on the end, it's cut off because we don't really add extra 0.0s if they're not there, right? If extra 0.0s in decimal form, we chop them off, but technically that's 0.00000, right? So the decimal point is right there. So let's count the number of spaces that we are moving it. Because again, remember, we need one place. We need this to be 9.296, right? There's only one number left of the decimal, and all of our other numbers are going to be to the right of the decimal. So I'm going to use red here. 1, 2, 3, 4, 5, 6, 7, right? So we move that decimal place 7 spots. Now I think they're gonna, that something should ring a bell there for you, but let's go back to the video, and it's asking us how many spots do we have to move the decimal? It's 7, right? So
write the number in standard form in scientific notation. The first factor in scientific notation is always a number greater than 1 and less than 10. So place the decimal point after the first non-zero digit. Count the number of digits after the decimal point to determine the power of 10.
So look, it's the same number, right? That's just kind of how we did it. I like the way they did it, actually. I'm going to go back to my Jamboard. They started and they said, okay, we got to make this number into scientific notation. So they just started out and put the decimal where it needed to go. Oh, that's not right. 296, right? And then they said, okay, how many places do we have to move the decimal to get back to our original number? 1, 2, 3, 4, 5, 6, 7, right? That would give us our extra 0. 1, 2, 3, 4, 5. I did something wrong here, but you can see where they're coming from here. They put the decimal point first, and they put it after the first number, and then they counted up the number of spots they need to move it. 1, 2, 3, 4, 5, 6, 7. What am I doing wrong here? Oh, it's okay. Let me just go back to this, and there we go. I'll just share this. Right here you go. 1, 2, 3, 4, 5, 6, 7. I don't know why I was struggling with that so much. Just bad art, I guess. I've never been a good artist. So they moved the decimal point 7 digits to the left to get it to be here, right? Therefore, it is times 10 to the 7th. If we have a positive exponent, we're going to move the decimal point to the left.
Why does the first factor have to be less than 10 in scientific notation?
Because if it was more than 10, then we would have to add a number in the power, basically, right? If it was 92.96, it would be times 10 to the 6th, because the decimal point would be here instead of here. So we always want to write it with only one number in the ones place to the left of the decimal.
If it were greater than 10, you could have used a greater power of 10 for the second factor. Both of Luis's numbers for the distance between Earth and the Sun represent the same distance.
There you go. So those two numbers represent the same distance, right? This number right here and times 10 to the 7th represent the same thing. Erase this. Get rid of that. Because that literally means if I take 9, oh, I got rid of my, if I take 9.296 and I move this 1, 2, 3, 4, 5, 6, 7, and add zeros for the blanks. Now I did it right. I don't know what was going on with my art first time. That's what I get, right? I get the same number here and here. I move that 7 spots to the right. It's a positive exponent. And I got the correct number. Oh, sorry, I forgot to share the tab at home, right? So let me illustrate that again in blue. I started out with the decimal point here, right? 9.296, just like in this one. And I moved it 1, 2, 3, 4, 5, 6, 7, because it's times 10 to the 7th power. And I got what I needed to get. So that's good, right? And welcome to those of you guys just getting here. We are going over scientific notation, which is kind of the next step in what we did yesterday with writing bases of 10. Let's go back to the video here and we'll start a try it. Or we'll start an activity. Select each factor to see if the number is in scientific notation. What do we think about these? I guess we just click on them. 5 times 10 to the 8th power. The second factor is times 10 to the 8th, which is a power of 10. So this is scientific notation, right? If we have one number left of the decimal, which we have right here, we only have one number in general, and then we have a times 10 to the 8th, base 10, then that is scientific notation, right? Same with this one. You have one number left of the decimal, and then you have other numbers in your decimal, and then times, oh, but look, this is times 4 to the 10th. It needed to be times 10 to the 4th. So this one is not scientific notation because it's not base 10. We always need base 10 because base 10 is what allows us to move the decimal point one place to the left or one place to the right. So here's one that is, right? 11.1. Oh, wait a minute. It's not because the decimal point should be here. Should be 1.11 times 10 to the 8th. Not 11.1 times 10 to the 7th. We can only have one number left of the decimal. So this last one is correct. This last one is 7.2948684 times 10 to the 3rd. Yeah, that is scientific notation, right? We have one number left of the decimal and then a base of 10. All right, so let's go on to our first activity here. And let me okay, so the height of Angel Falls, the tallest waterfall in the world, is 3,212 feet. How do you write this number in scientific notation? So, how many spots do we need left of the decimal in this number? How many, if we're going to write it in scientific notation, how many numbers can be left of the decimal point? We were just talking about that on the last slide. Can I put 32.12? Is that possible?
Let it rest. Wait, what'd you say again?
How many places left of the decimal do I need to write this in scientific notation? Can I write 32.12? Oh, 32.12 times 10 to the something? Is that in
Yeah.
scientific notation? You have to only have one place left of the decimal, right? Our decimal always have to go after the first number. So this is not correct. I need to have, I'm going to start out by saying 3.212. I don't know why they only gave us 2 blanks, but I have to start out with 3.212. So 3.212. Now we got to figure out how many spots do we move the decimal, to make 3,212. How many spots do I have to move the decimal? Well, let's count. 1, 2, 3, right? To move the decimal here to make this number, we moved it 3 spots to the right. So we would have 3.212 times 10 to the what? How many spots do we move the decimal? We just did it right here, guys. Make sure you're watching. 1, 2, 3 spots, right? 1, 2, 3 spots. So we would put times 10 to the third, right? No, I have it. That's what I'm using. So this number right here represents 3,212, right? Right here. That is our answer. 3.212 times 10 to the third. Anytime you see a times 10 to the third or times 10 to the positive exponent, we know we're moving the decimal to the right 3 places. 1, 2, 3. So that would give us 3,212, which is our original number, right? So that's how we're doing this. That's how that's done. All you're doing when you see times 10 to the something is moving the decimal place. Positives, you're moving the decimal right. Negatives, you're moving the decimal left.
Mr. Levine,
Yes.
it's 8:58.
We're on regular schedule today, so this class goes till 9:15. Yeah, we're not on the hour schedule. That's only Mondays. All right, let's go on and try some other ones here. Let's do one with small numbers. All right, what is the width of a red blood cell written in scientific notation? So I'm going to go to the whiteboard because it's not going to let me write on this. How many zeros are there? 1, 2, 3, 4, 5, and then 703. This is 0.1234 zeros, and then 703. How are we going to write this in scientific notation? All right. So the first thing we need to do is pick out our numbers that we need to write to start out with. What are you going to start out with when you're writing this in scientific notation? It's going to be something times 10 to the something. What is our 3 numbers that are actually numbers? A 703, right? We're going to take these numbers right here. That is going to be what we start with. So let's put those down here. Now, where does our decimal point need to go? How many numbers can we have left of the decimal in scientific notation?
1.
You can only have 1. Good. So I need to put my decimal point right here. So now we have a start. We have one number left of the decimal, and everything else is right. Now we need to figure out what our exponent's going to be in our base 10. So in this number, our decimal point would be here, right? So how many spots between here and here? Let's count them up. I'm going to change to blue. 1, 2, 3, 4, 5, 6. Right? Everybody agree that that's 6 spots? So the exponent, I'll just use that in blue, is going to be 6 spots, but we went left. Remember, on the number line, left is always negative, right? Right is always positive. So this is going to be times 10 to the negative 6. If you see times 10 to the negative 6, you're 7.03, and then you're moving this point 1, 2, 3, 4, 5, 6. Move the decimal point and fill in zeros, right? Isn't that the same number? These are the same numbers. If I start right here and then I have a negative 6 exponent that causes me to move 6 spots to the left, and I fill in those spaces with zeros, I get the same number. All right? So that's all you're doing. If you see times 10 to the something, you are moving the decimal point. Positive goes right, negative goes left, just like a number line. So let's see if we got this right. We came up with 7.03 times 10 to the negative 6. Oh, it's not going to let us. That's weird. I don't know why it didn't let us. Oh, all right. Now it's going to, I see, it's going to do it on screen. We move the decimal point past our first number, right? 7.03, because we need one number to the left of the decimal. That's between 0 and 10. Well, it needs to be between 1 and 10, really. And then they counted up 6 digits, right? There's 6 spaces, just like we did. 1, 2, 3, 4, 5, 6 to get there to our new decimal point. So we know it's times 10 to the negative 6. There you go, 7.03 times 10 to the negative 6 meters. All right, let's do a try it. Yes. That's fine. You can put it in one of these cubby holes or something. Do it later though. I'm recording right now. So a common mechanical pencil lead measures about 0.005 meters in diameter. How can you express this measurement in scientific notation? So let's go to it. What's our number? What's our one digit going to be? We only have one number in this that we need. What is it? Right, we need one number left of the decimal, but what's that number going to be in this number right here? What's the only number that's not 0 that makes any difference? 5, yes.
5.
So we start with 5. We don't have anything else. If this was 0.00512, then we would have 5.12, right? But it's not. So we can get rid of all that. It's literally just 5. This is going to be a really easy one. Now, how many spots do we move the decimal here?
2.
2 spots, right? 1, 2. Oh, actually, it's 3. Look, to get to here, this is our new decimal spot, right? We moved it 1, 2, 3 spots, right? So we are going to have, this is going to be 5 times 10 to the negative 3. So again, if I write this, I'm gonna carry this down here. If I have 5, the decimal point's right there, right? It's 5.0. I move it 1, 2, 3 spots. Here's my new decimal point. I fill in the 2 blanks with zeros. That's our original number, right? Same thing. So we moved it 3 spots to the left. So we have negative 3. The negative ones are a little harder than the positive ones. But that is how that's done. 5 times 10 to the negative 3. Let's see. Let's convert one to standard form, and then we will be about done for today. Kelly used a calculator to multiply large numbers. How can she write the number on her calculator screen in standard form? So what this means, this E means times 10 to the 15th, right? 3.5 times 10 to the 15th. That's what that means. Some calculators will write it that way. So 3 times 10 to the 15th. That means, or 3.5. That means we take 3.5 and we move it 15 spaces. 3.5 times 10 to the 15th. So we're taking 3.5 and we are going to move this decimal point 15 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we got to fill in zeros for every single one of those blanks. I don't even know what that number would be called. It's so big. All right, we asked what's bigger than a billion yesterday. It's like a quadrillion and stuff like that. And then it goes on and on and on. I don't even know what that number would be. It's so big, right? So there's the demonstration, right? I forgot to click over for those at home. I moved this decimal point in this 3.5. I moved it 15 spots over and I filled in all the zeros. This number is what they get on the original. That's what they got, right? It's right here. Times 10 to the 15th means we took this decimal point that was at 3.5 and we moved it 15 spaces to the right and filled in all the zeros. So that's a really huge number. So again, that's why we use scientific notation. It's easier to write this than it is to write this with all these zeros. It just takes too long to write all the zeros. And it takes up a lot of space on paper or on a screen, right? The calculator on this would run out of numbers. If it tried to give you this whole number, it would run out of numbers because most calculators only have either 8 or 10 digits. So the calculator says it's 3 times 10 to the 15th, and it can actually give you the actual value instead of having an error. So here's 8 times 10 to the negative 9th. I'm going to go to the whiteboard. Let's clear this out. 8 times 10 to the negative 9th. We're going to take 8, right? It would be 8.0 technically. So the decimal point's right there. I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9. My new decimal point's going to be right here. And I'm going to fill in all these blanks with 0, 0, 0, 0, 0, 0, 0, 0, right? So our new decimal is 0.0000008. So that's what that is. Let's go back and check it. Here's what they did. Times 10 to the negative 9th. They moved it 9 places. They took the decimal here. They moved it 9 spots over to the left because negative is left. And then they filled in zeros, right? Again, it's a lot easier to write 8 times 10 to the negative 9 than it is to write this. So again, negative numbers in the exponent will make small numbers, right? Really tiny numbers like this, really tiny decimals. Positive exponents will make huge, gigantic numbers like we did on the last question. We will come back to this and we'll do this tomorrow. But make sure you guys check on Savas. There are assignments on Savas about bases and exponents and scientific notation that are posted. So we're almost out of time here. We got about 2 minutes left. So I'm going to shut the recording down. But please make sure you guys are checking your Savas and doing that homework over the course of the week. All right, Brandon, you can get off. And those of you in class, we're almost out of here in 2 more minutes.